So I will start directly with a summary, and I think you heard a lot of information already from Jean. We worked side by side for the last 6 years with Peter's lab, basically also in the last years tackling this large ENSO-E system. So our core topic is this dynamic stability of the future in ENSO-E system, in particular when you replace synchronous machines with renewables from converters. I will talk about the kind of disturbances we investigate, and the complementarity to Jean's presentation is basically we also have tried to take lessons from small systems to big systems. The difference is we look at single large disturbances, in particular islanding scenarios, as a complement to the oscillation information that he extracted from the model, and give you some insights. And in this direction, we also worked on a new dynamic simulation framework to tackle the tasks at hand with this big model. We, in the end, also put an investigation effort into the difference between the types of renewable models that you have in the system and what the impact of the stability is. And as for the results for a wide range of scenarios that we tested, I will show some look into stability conscious as a service to the grid operator. I will tell you about the results of these different converter models, and I will give you some further insights we could extract from this complex model. So first, I will talk about this dynamic simulation framework, and the quick background is basically the stability of the ENSO-E system and what are the challenges in the support coming from the converters placed all over Europe, basically, and also what could happen when the situation changes during the day. You have a lot of converter-based generation coming over lunch here from the south with a lot of PV, and maybe more in the evening from wind farms in the north. So you have this load flow dependency aspect. And basically, the large disturbances we picked as a reference in accordance with Swissgrid is based on the 2006 islanding event. So it's not the loss of a single unit somewhere in the system, but in the end, when you have such an islanding event, it's tens of gigawatts that are suddenly lost in each of the zone. And we took a look into it, how the system reacts to this. Basically, the framework here is using an import module to access the data we got from ENSO-E and the power factory model. We have this modularity aspect where we can introduce a lot of components, and in particular for this project, also converter types. And then post-processing investigation we can do after the simulation is carried out. And a rough estimate of the complexity is for this big model that has 10,000 buses and about 1,000 generators, it's about real time when we run it. So 1 minute takes about a minute, but when you have the event directly after the event, it takes a little bit longer, of course, for the integration. So the workflow, one slide on the technicalities. I want to give some few insights. So it combines symbolic differentiation of the component equations to analyze the structure of the simulation problem. Then after this is done and compiled into C code, waiting for parameters like what is the inertia of the generators and so forth, this parameterization is handed over and assembled. It assembles the individual components to a network model. And the dynamic initialization that we have to perform, for instance, for different load flow scenarios in the European model is pretty tricky because it depends on that you first of all provide feasible voltage and reactive power set points to the problem. So there we applied a two-step solution. First, we converted to an OPF problem and determine reasonable settings for the reactive power and voltages. And then we solved the dynamic initialization problem. So usually you try to solve it directly without this first step, but for this large problem, we had to introduce this step. And afterwards, we post-process and extract the performance metrics we are interested in. So here, this is a base case when you download the file from ENSO-E that you get and apply our system split. So basically, we have here the three zones, again, the southwest, southeast, and the north that were colored in the previous map. And you see that there's some overproduction here in the southwest, so the frequency increases a little bit. And here, in total, these are the 1,000 generators in the system. And there are some static generators also that are modeling some existing PV or renewables in the system, but nothing added from our side. So this is the base case, basically. And the metrics we extract, one I will use in this presentation is the rate of change of frequency, which is it's roughly estimated if you look here at the classical swing equation. It's basically how steep the slope is of the average of these frequencies in each of the plots here. And to estimate it in accordance with SwissGrid, we used a rather longer time window of 2000 milliseconds, so 2 seconds. Then this base case is modified in 2 important ways. First, we change, let me jump back, we change the power exchanged here between the areas. So for instance, shifted from the south to the north or from the east to the north or vice versa. We didn't change the loads of the system because it's already a high load scenario, but we modified the generator settings. And then after this is done, we allow for new renewable energy to be included by shifting from synchronous machines to converters. This is kind of the look into the future when part of the production or an increasing part of the production is provided from renewables. So regarding the modeling of the renewables, I want to give some insights here, what we have looked at, because I think this is one of the takeaways that can also be applied to many other projects simulating transmission grids. Very often, in large and complex systems, renewables are modeled in a rather simplified way to allow for tractable complexity of the overall problems. And we encountered very often the impedance models that are used for this converters. So basically, if you inject active and reactive power, you provide an equivalent impedance, negative impedance that provides the same power in the steady state. But in dynamic situations, there are important differences, and we wanted to see what the differences are and what are their impacts on the takeaways when you assess dynamic stability of the system. So we compared to 2 types. Basically, the equivalent comparison from IMP, IMP, to C is a CCC, the current controlled capacitor. Basically, there we have just a very small DC capacity and the power set point basically coming from uncontrolled reference. And the goal is to keep the DC voltage at the reference point. And this is basically how most PV converters, for instance, without additional storage would operate in a dynamic setting. And then if we take away all the synchronous machines in Europe, say above 50% or so, some dynamic support that traditionally comes from the synchronous machines has to be taken over in some form or the other from the converters as well. And this is a topic of research and debate, how to best tackle this support question from the converters. We picked here a rather complex one, a virtual synchronous machine model, basically taking over as many tasks of the synchronous machines as possible. And for the short moments after a disturbance that we investigate, basically we have a constant DC voltage, because power is not only coming from a source but, with a constant power, but also battery storage that is flexible. So as I said, the IMP model is often used for complex systems, and we will now look at how realistic are these models compared to the CCC, and what is the potential you can gain if you add dynamic support from the converters. Basically, here's an overview of this converter structure, VSM. So there you see there are a lot of blocks, control blocks here, setting virtual impedance, Q control, and P control, basically setting the set points of the converter based on the measurements they receive here from the system. So here's an aggregated summary that we computed for a small system, the Kundo system that you saw in the previous presentation as well. Basically, we shifted the generation power to converters located at the load and sampled values here from 0 to, I think, 800, about 800 megawatts. And the red line is just the base that you have without any converters, and the yellow line is what you would get if you shifted to a CCC converter. And you see, I want to guide your eyes to the difference between the blue line and the yellow line. Basically, the blue line shows you how the Rockoff increases with an impedance model, and the yellow line shows you the increase you get of the Rockoff with a current-controlled capacitor model. And you see that it's more than twice as much the increase that you get for additional power shifted to converters. You can regain some of this difference by adding, of course, dynamic support, but still, even with VSM converter and battery storage, you still have a higher Rockoff in the dynamic situation than you get with a estimated or simplified impedance model. So the rate depends on the converter type, and actually we computed something that we call a Rockoff premium. So basically, if you say that for additional power from renewables in the system, the Rockoff is increased with a certain slope. So the K is basically the slope you would get, for instance, for the impedance model. The current controlled capacitor and the VSM actually have a larger slope than this. And this numbers 2.6 and 1.5, so 50% larger and almost, well, 160% larger here than the impedance slope. These were validated for a wide range of load flow situations, power balances in the system, and parameter settings. So the absolute numbers of K change, but this ratio stays more or less the same. So you can use, as a takeaway, you can use this increase to reassess existing results that you got from a project where you simulated the system with the IMP models, basically the negative impedance models. And you can see if qualitatively your lessons to learn from this change under that update. So now I want to show you how we apply it. This and other things to the large power system. And basically, here in this slide, I show similar aggregated results we obtained for the NSOE power system. So here, in this slide, you see on the y-axis again the average Rockoff value in one of the zones. In this case, it's the southwest, so Spain and so forth of Europe, as a function of the generation power added to the region. So you see that if I add 10 gigawatt of generation to the, so I increase the generation in the region, basically the Rockoff will increase from this Rockoff you have here in the base case at 0 to a certain value that is larger. So it will, in this case, go from about 0.05 hertz per second to 0.25 hertz per second when I add 10 gigawatts of production in the area and keeping the load the same after the system split occurs. And the slope of this almost linear behavior here increases if you have additional renewable energy in the system coming from converters. And it very nicely relates to this simplified swing equation you have in the system. So basically the generation shift increases basically the mismatch between power production and power demand in the area, so the delta P. And if I shift to renewables and I go from 0 to 40, which would be this solid group of lines to this dashed group of lines up here, you basically decrease the inertia in the system and so also increase the Rockoff. So it's 1 over the inertia. So similar patterns you see in the other regions with different slope depending on the power balance and the converter, the generation settings in the region. But in aggregate, you also have this linear, roughly linear behavior, and this allows you to do some interpolation and to update these coefficients with this Rockoff premium that I showed before in the previous section. So you can estimate the Rockoff now for different shares and types of renewables models without further simulation to get a rough estimate of the behavior. And then you can go even further, because what you want to know is my system secure or not. And to this end, basically, we propose here a summary of the results and a visual summary that shows a stability control for the grid operator where your system is. So it informs you, for instance, when the system approaches a risky state. Let's say a limit is, for instance, you don't want to go above a rock-off of 1 Hertz per second, and you can monitor where you are. So here you see one basically power balance in the system, and after the system split, you see how the rock-off would change if you shift power to CCC converters, so PB converters basically, and if some of the power is also shifted to VSM converters. So you see, for instance, for a rock-off limit, let's say here the green line of 0.75 per second, you could shift about 70 gigawatt to from the synchronous machines in the southwest to CCC converters. Or you could shift more than that, so 125 gigawatts to converters with VSM support. In both cases, however, we have updated the results that we received from the simulation with the impedance model based on this rock-off premium, because it's too optimistic, the impedance model basically. So you can create this for a wide range of load flows and events and intersect it also accordingly. And this could be a complement, for instance, to the N-1 monitoring that the TSO is doing in the control room, to see also that there's a dynamic critical state or potential state arriving or approaching in the transmission system. So not critical, but risky. So one final insight I want to share with you that we found during the project is that it's not just the rock-off, of course, that is of importance, but also the stability, not just the average in the region, but also the stability in the region. And sometimes, depending on the distribution, this becomes very impressive. So here you have in the simulation an emerging of synchronous clusters that is already seen here at the beginning when a group of generators starts to deviate. So actually this you see here on the left is Spain and Portugal decoupling from the rest of the Southwest. So the Southwest is splitting into 2 zones. Of course, there we didn't have the protection implemented, but you would basically open the lines between Spain and France the moment you hit about this angular difference over here. And this we have simulated this protection here on the right side. So you see that the 2 clusters now, Italy, Switzerland, and France, and Spain and Portugal are now separated here. And this cascade of basically islanding, you can also identify from the regional frequency cluster that we obtained from the simulation. So we have written some routines on that and are further investigating this. With this, I just can show you the same summary I showed in the beginning. So main takeaways here, we can compute stability contours for the complex system. It's important to note that the impedance model will likely underestimate the impact of converters on dynamic stability. So look into this if you use impedance models. And with this simulation, you can get insights in dynamic couplings and cascaded outages. I thank everybody for the attention and would be happy about questions.